So let's get going here with the discussion on sequential circuits. So last class we were discussing the idea of a latch and a flop. A flip-flop is also called a flop, right? So this is level sensitive and this is edge triggered. Okay. So we also discussed one very simple implementation of a latch, which is using a multiplexer, right? So if you look at the latch, if, right, and by default it's a positive, it's sensitive to the positive cycle of the clock. So if clock equal to 1, then Q equal to D, else Qn plus 1 equals Qn. Hold the state, right? So we said that we can implement this very easily with a multiplexer, and if you want a positive latch, then what you have to do is you have to allow D to go through when clock is 1. And this is 0. Okay, so using this, we now want to construct a flop which is going to be edge triggered. Okay, so we'll see how we can do that. So if this is a latch and it's a positive latch, then the basic idea is you cascade 2 latches. Okay, let me call this QM. Clock, clock. Okay, I'm going to call this clock only, so we have to fill the 1 and 0 here correctly for the mux. This is Q. Okay, this is a flop, and I want it to be positive edge triggered flop. Okay, so now the question is, what kind of a latch should I put in the first stage? What kind of latch should I put in the second stage? Negative in the first stage and positive. So 0, 1, 1, 0. Correct? So what we'll do is we'll draw a, maybe I should just select this. Okay. So we'll sketch a timing diagram to understand how this actually works. Okay, why we should put a negative latch in the first stage and a positive latch in the second stage, right? So by the way, this is called the master stage, and this is called the slave stage. Okay, so let's assume my clock is like this. Okay, and my D as usual makes some transitions before the clock, after the clock, and so on. Okay, I'll make some transitions here. So this is D1, D2, D3, D4. Okay. So now what happens when the clock is 0 here? Okay, this is let me call this latch L1, L2. Okay, latch L1 and latch L2. So first of all, in each phase of the clock, when clock is 0, tell me if L1 is transparent or opaque. L1 is, when clock is 0, it's a negative latch. So clock data has to go through. So therefore it's going to be transparent. L2 will be opaque. It's a positive latch, right? So positive latch means in the negative cycle is opaque. Data cannot go through. Similarly here, L1, L2. What's happening here? Huh? It's reverse. Opaque and transparent. Transparent, L2 is opaque. Okay, and this continues. So what we want to now see is, how is it that we are able to put two level sensitive latches and still make it an edge triggered flop. Okay, so let's see what happens to D1. D1 is, changing in the 0 cycle, during which L1 is transparent. That means any change in D will go through or percolate to QM, right, to the output of this thing. So QM, we can safely say, is, this is D and this is clock, is D1. It may have happened with some delay, but given that D1 has settled already, this is going to be D1. Okay, now D makes a change to D2 before the clock edge. Okay, so what is the sampling edge for L1? Yeah, if it's a negative latch, then it's a positive edge. That's going to be the, so therefore if D1 switches to D2 at least a setup time before the clock edge, then this sampling will happen properly, right? So which means that I'm not going to worry about the contamination delay right now. Okay, I'm just going to make it like this, D2. QM will now change to D2. What happens to the change of D2 to D3 for L1? It will remain, because now L1 has become opaque, right? And therefore it's going to keep D2 all the way until L1 becomes transparent again in the 0 cycle. So therefore here you will see a change to D3, right? And there are obvious things where if D1 changes here, this is the edge, this is the transitions that's triggering the change in QM, right? Because L1 is transparent, change in D goes out to QM. On the other hand, when the clock goes low, that's when the L1 becomes transparent, and therefore this is the thing that will trigger a transition to D3, right? We are consistent till here. Now we have to see what happens to QM. Okay, so in the 0 cycle, what was the state of L2? It was opaque, right? So that means it's holding some state, so we do not know what it is. So that's why we said, remember that this thing we do not know what it is. Okay, we don't know what the state is. It's an unknown state. Now the clock is going high, and therefore L2 is becoming transparent and L1 has become opaque, right? But QM has already sampled D2. the latch L1 has already sampled the data that you wanted and it is holding it through the positive cycle. At which point L2 is now becoming transparent, and therefore the change in D2, this thing, D2 will go out. Okay? Which amongst the change in QM or D or clock, which one is triggering this switch to D2? It's the clock, because the clock is now switching and making L2 transparent. It was opaque till now. That's why this is happening. The delay is basically whatever TPCQ or whatever, right? We'll come to that. Now what happens to the change that of QM from D2 to D3? L1 is transparent, but L2 is opaque. The moment the clock goes low, L2 becomes opaque, and therefore it is going to retain the state. What is that state? D2. So it's going to simply retain D2 all the way till here. And eventually you will see the same thing, because now D3 has changed. Of course, L1 is transparent, so therefore you will find a change. No. So QM, it changes to D3, but then it will also switch to D4. Correct? Yeah, that's right. D4. Okay, so maybe I can move this clock a little bit. Yeah. So assuming that happens, then at this edge again, you will find that it switches to D4 successfully, right? And so what you see for a flop is basically only clock, D and QM. Q. You don't see QM. And that's why all the changes are happening with respect to the clock edge. Right? So now let me just ask you a question. What is TPCQ of the latch? I mean of the flop. Assume that the latch has some parameters, TCCQ, TPCQ and all that. What is TPCQ of the flop? Huh? You agree that this delay is nothing but TPCQ of the flop, right? Let me call it flop. What is that delay? Q of the, in terms of the latch delay component. Exactly. It is TPCQ of L2. It's just how long it takes for data to go from input from the clock going high and making L2 transparent to the data being available at the output of L2. Right? What is the setup of the flop? The setup of the flop on similar lines. Setup of L1. Okay. So basically what is happening is L1 and L2 are operating alternately in this transparent and opaque mode and achieving this edge trigger business for you, right? Because L1 is transparent. Basically, if you have to sample on the positive edge, then the first latch should be transparent in that previous cycle. That is when the clock is 0. Only then you can sample and then hold that data, right? So clearly the slave stage does nothing. It basically just takes the sampled output at QM and just holds it for the remaining part. Okay, so if you look at what is happening in this D2, right? L1 is actually transparent, correct? L1 is opaque, L2 is transparent. So what is happening is your QM is being held for half the cycle. In the other half, it is Q that is being held. Ultimately, you want a flop to hold the data through the entire clock cycle. How is that achieved? That's achieved by holding the data on L1 for half the cycle and holding the data on L2 for the other half. When data is being held on L1, the slave is transparent, right? And therefore data just goes through, correct? When L1 is opaque, it is in hold mode. L2 is transparent or allowing the data to go through. So L1 is holding the data for the positive half cycle, L2 is holding the data for the negative half cycle, and that's how you achieve edge triggering with 2 level sensitive latches. Okay? Any questions here? So now you just look at it, okay? What is the setup time of the flop? Basically, the data has to change before that sampling edge, right? What is the sampling edge? It's basically this positive edge here. Which flop is sampling the data there, or which latch is sampling the data? It is L1. See, L1 is transparent here. Then L1 is becoming opaque. Now L1 is sampling the data and holding it. Why TPDQ? So PDQ is of the first latch. TPDQ is basically this delay, right? This TPDQ, isn't it? Okay. So we'll come to this. We'll see where the origin of this setup time itself is. Now that is nothing but some delay of the first latch. Okay, so we'll come back to it. I'll answer this question maybe in the next class, where we look at an implementation and then we see what needs to happen, right? And the origin of the setup time first of all. Why should I even have a non-zero setup time? Once we look at that, I can answer that question more clearly. Right now, I'm just saying, if I give you a latch with a setup time value, you can express the flop setup time in terms of the setup time of the latch and the TPCQ of the slave latch. That's all I'm trying to convey here. Okay. So anyway, so let's now look at some circuit implementation. Right, we drew a very simple picture here. We said we put a mux like this. We are going to hold the data through a feedback, and the clock will be the select line. Okay, so this is what, let's say I want a positive latch 0 and 1. So how do I now implement this in circuit level? The best thing to do for a multiplexer is, what's the best circuit implementation for a multiplexer? transmission gates, right? Pass transistor is just one NMOS or PMOS. Transmission gate is a combination of them put in parallel, right? So obviously we'll do this. Q. Okay, so this is my D. So can you tell me what this signal here should be? Should it be clock or clock bar? Corresponding to this latch, positive latch. Clock, clock bar. When clock is 1, right, we want the D to go through, right? So when clock is 1, this has to be 1. Therefore, that has to be clock bar, and this also has to be clock, right? Clearly, we have a, it's okay, it's a very simple implementation, but like I told you, a transmission gate without a driving gate is meaningless. Because I can't tell you what the delay is, I need to know which guy is driving, I can't even characterize this flop. If I want to say that this guy has a setup time of so much, and this has a PCQ of so much, then I need to know which gate is driving this in order to tell you this delay. So that's meaningless. I need to have a standalone flop that I can just characterize and say that these are your setup, hold time, and clock to Q delays. Go ahead and use it in the circuit. For that, I need to now put in inverters so that we can use them appropriately, right? So what do? We are simply going to break this circuit and put inverters in the path. First, I put one inverter here. Okay. Then so what do? I can will that work? I don't think so. So we do this. So this is the output. Yeah. Yeah, loop 2 inverter should be there, right? So this is not a correct implementation. That's right. So therefore, this will satisfy my 2 inverter requirement here, right? And of course, I can do this. No, but again, this cannot be driving here. It has to appear here. Because, yeah, you can wire or only the outputs of a transmission gate. So I cannot connect this to the output of the inverter because that will always be driving something, and I cannot wire or something there. So the wired or connection should always happen at the output of the transmission gates. So this is TG1, TG2. So only those outputs I can wire or, and the remaining cell. So what you can do is, if you want, you can really avoid this guy and take your output here, right, or Q as I would call it here. Yeah. Okay, this is a very simple circuit implementation of a positive latch with inverters and transmission gates. Okay, so yeah, we are out of time. So in the next class on Monday, we will exactly determine what the setup time and clock to Q delays are for this kind of an implementation. Okay, and hopefully his question also should be answered at that point. Okay, so just be very careful. Sometimes you can get confused if you don't practice this hard enough, where like I did now, you might put the connection here. That can't happen. Remember, wired OR connection has to happen at the output of the transmission gate always, nowhere else. Okay.